about this. So you realize that we have only that's the recording. That's we have only 2 chapters more. So maybe we'll finish them. We'll finish this semester early, or maybe very early. I don't know, but early at least. We'll not be stuck until the last second doing things, but we'll have a lot of review. So anyway, so we went to classification and went to the last classification. We did the maximum solubility, saturated, supersaturated, I remember, and then stuck solution, normal solutions, correct? And the last classification of solutions is depend on osmosis. So the osmosis here, as I said, and somebody answered that question when I asked what's osmosis all about. Osmosis is the diffusion of a solvent from higher concentration to lower concentration. Can I have reverse osmosis? Yes. I have to put pressure from outside to get this diffusion from lower concentration of the solvent to higher concentration. This process requires a lot of energy, a lot of money, because those filters, especially in the desalination, but they call it desalination, means taking the salt out of the sea, hard H2O, and make it sweet or soft H2O, drinkable. You cannot drink sea water, because what will happen is you'll have large concentration of calcium and magnesium, which can cause death, correct? Too much, the concentration is very high. So they use the reverse osmosis and get the sweet or soft H2O out of the hard H2O, which is ocean H2O. Anyway, so, and according to osmosis, we can differentiate between 3 types of solutions. Somebody has taken this ALP, this experiment in the lab. We have isotonic, we have hypotonic, we have hypertonic. Isotonic, when the amount of the H2O inside and outside the cell is equal, nothing changed. And it's a typical cell will have this, it has a lot of other ions, but the most important one is typical cell here, red cell. Around 5% sugar, about 0.9%, which is close to 1%, is sodium chloride. And the rest, if you wish, the rest is about 94% H2O. That's a typical major contents. And you might have other electrolytes or something, but it's very, 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 very tiny, small concentration. But those are the major 3 components inside the red cell. So now, usually the sugar does not change in content. What's really changing in content, those 2 here, the amount of those here. Okay, so we can see, if this is the red cell here, let me make it maybe red here so you can. The red cell here, this is a red cell here. What's happened is, you can imagine this is a red cell here. So the red cell has all those 3 components, some other components as well. So, but those are the major ones. Now, if H2O outside H2O outside, this is outside, and uh, H2O outside here, and this is H2O inside, sodium chloride inside. Of course, sugar as well inside. So now we are interested in those two here. If the H2O outside is say 94% and outside is 94%, so we speak about healthy cell, healthy cell, healthy red cell. So this one here, this case here, outside H2O amount equals inside H2O amount. So we speak about isotonic. Isotonic solution. And this is a healthy cell. And we can say this is isotonic red cell, isotonic solution or isotonic red cell, which is the cell is healthy, whatever H2O outside equal the H2O inside. And the amount of sodium chloride is the same, it's not changing. You have about 1% or 0.9% H2O sodium chloride and about 1% sodium chloride. This is outside. And inside the same thing. So this is healthy cell, but it comes sometimes to the diseases. That's through this is natural happen. This is mostly here natural. It's nothing, you're not forcing anything. This comes by itself. So, and that is the normal healthy situation. But it comes sometimes we have diseases here. Everybody has this? Everybody has this? Everybody has it? Okay, so let me take this one out. It come in cases that we have two cases here. This is a red cell. This is another red cell. Well, what's happened is this red cell here can shrink, like, or can be expand here. Can be expanded or can expand. So let's say shrinks, expands. So it really expands and you get something looking like swollen up like this, bigger than what you started with. So this case, then you have the H2O. We said H2O goes from what? Higher to lower, correct? When it shrinks, that means H2O diffusing outside. Are you following me? You don't have to memorize. When it means shrinking, it becomes very small. That's whatever H2O inside going to outside. So the diffusion, normal diffusion from higher to lower. So the H2O inside is higher than 94%, about 94%. And H2O outside is lower, correct, than H2O, inside. Okay, guys? And the assumption that the sodium chloride will be is the same thing. It's changing. So main thing is we are looking at the H2O. That's affecting the shrinking, and the swollen is not affected by sodium or sugar. It's affected by the amount of H2O coming in, amount of H2O coming what? Out. So that's type of shrinking called kirination. The disease is the illness or disease called kirination. That's cremation, kirination. So it's not you are burning a dead body, but it's no, it's kirination. CRENAITON. I might have not correct spelling. Just, as in medicine, there's a lot of illness, a lot of pharmacy, medicine. Even the doctor sometimes it's not. My doctor was very funny. It comes sometimes long, and then he said the three alphabet. Then he said to me like this. So the three alphabets, and you cannot pronounce like 17, 18 alphabets in one medicine. And we were talking about it, and I was laughing at it. But anyway, so this is a small alphabet. That's just about 6, 7, 8 alphabet. So let's look at this one here. First of all, everybody has the one we have. Can I take one? We come back to it. We'll come back to it. But here it is. So this one here is when you have this is the H2O inside the cell is very high. So I know that you can't memorize all this, and I don't want to memorize. I want you to understand what is really why is forcing H2O coming out of the cell, and the cell will shrink. When the cell is shrink, the disease. Oh, I spell it good. Oh, it is not Monday for me. It is Tuesday today. So I spell it correct. CRENATION. It's not some other diseases like 15, 16 alphabets. Those are Latin. Most of those diseases are Latin, and there's too many alphabets inside. But that's English. Kirination, not cremation, kirination. I have a student said cremation. Cremation is burning a dead body. So anyway, so this here, because the H2O will diffuse out, the cell will be, and if you Google the picture, looks very, very scary, like spooky, like Halloween. You can see the bones, because all the water is out. Because what's really making the size of this H2O? Over 80% of our body is H2O. You take the H2O from the body, and you can see then the bones, the structure of the bones. I mean, it's just so. I mean, this is a disease. And the solution now, it has hypertonic. So the main thing is you concentrate yourself on the water inside the cell, outside the cell. If you know this, inside and outside, that will give you a lot of information. And always diffusion is from higher to lower. From higher to lower. So you are losing a lot of H2O, because the body you can see is the skeleton of the human there. And I will look at this. So, and the amount of if you have higher H2O, then the amount of this will be less than 0.9%, correct? Will be less. Sodium chloride will be less than 0.9% or less than 1%, because most of the stuff is taken by H2O. H2O is more. than 94. So this type of solution called hyper. Hyper means always hyper, and you have hypo. Hypo means lower than. Hypo, YP. Hypo means hypothermia, hypotonic. Hypo means under or less or lower. Hypo means lower, and hyper means higher. So higher H2O, lower H2O. Higher H2O, where inside all this is controlling the H2O inside the cell. Inside the cell. So the hypo is lower, correct? And lower cannot go this way here. That's a reverse osmosis. Cannot go this way. It has to go where? It has to go from higher to lower. Outside is higher, so it will go like this. And the whole red cell will be what? Blown up. And it will come to the point that H2O will come in and in and in into the whole red cell will rupture, will be just like a balloon. You keep pumping gas or helium or argon inside the balloon to the point that the whole balloon will explode, correct? And the same thing with the red cell. You keep adding, then H2O, then the red cell will rupture, and this type of solution called hypotonic solution, and the disease is called hemolysis. I could not see a picture of this. I tried. I could not see a picture. Maybe in the dictionary of medical dictionaries you can find the pictures of hemolysis. But I saw coronation was very scary. The person looks like a spooky person, like literally Halloween skeleton type of person, because the whole body is losing 80. I mean, the red cells are losing a lot of H2O outside the body. So anyway, so those are the ones, the three ones. The healthy one, isotonic, in and out H2O amount is the same. We concentrate about H2O. Why? That's the most important one than the sugar or sodium chloride, because that's the one is diffuses easily, going in and out the cell, and that's what caused the shrinking and expanding of the red cell. So those are type of solution according to diffusion: isotonic, hypotonic, and hypertonic. Remember, when you have H2O inside, for example, higher means you have lower amount of sodium chloride. When you have it inside or outside, you have inside H2O is less, and therefore the sodium chloride will be higher a little bit. So the amount of sodium chloride will depend on the amount of H2O. Really, what's controlling the diffusion is the definition of the osmosis. Sodium chloride is solute. Sugar is a solute. What is a solvent? H2O. And the diffusion, the osmosis will tell you diffusion of the solvent from higher to lower. Not the solute, but the solvent from higher to lower. And that's what's really important for us. So we have hypotonic, hypertonic, isotonic. Hypo, less inside the cell, H2O. Hyper means higher amount H2O. Okay, guys? So I think that will be good. So next, any question you have? Any question? We'll go and look at solubility. Any question? Good? Okay. Very quiet. I know that's Monday today. This is good. It's good. Very quiet. Class is very quiet. So, well, we'll talk as solubility. Well, solubility is the ability of a solvent to be dissolved, solute in the solvent, correct? Well, this is the solubility definition. So the solubility definition is ability of a solute to be dissolved in a solvent? Well, this one here, whoever with me last week, we did this experiment. Today we'll have this experiment for the Monday section, and the rule is like dissolves like, correct? So a polar solution is made of a polar solute and polar solvent. And polar solution, so polar solution is made of polar solute and polar solvent. And we can tell that's unpolar solution is made of unpolar solute and unpolar and unpolar solvent. Okay, guys, that's what we did last time. Last week with the section 062 in the lab, if you remember. Those who are with me in that section, we did that, correct? So, an example of polar and unpolar, we did that in the lab. Can I take this one out? Can I take this one out? Everybody has it? Everybody has it? So let's take this one out, and we did say that the example of the polar solution we have, or polar solutions in the lab last week, if you remember, we have our solvent is H2O, and our solute, we have three different compounds. Two of them ionic, and one of them is covalent. Correct? We took a solvent is H2O. That's polar. Remember, H2O is polar. And then the solute, we have dissolved this one here in potassium nitrate. That's the first one. A second solute, we took it in potassium permanganate. And if you remember, those are ionic. Those are ionic compounds, correct? And then the third one is non-ionic, which is sugar, glucose, correct? And glucose has the molecular formula C6H12O6. So it has C6H12O6. That's a sugar. So this is covalent. But it's polar though. The only difference here, when dissolved in H2O, no ions are produced. That's the only thing. The polar covalent, they don't produce ions. Not all of them, but the non-electrolyte ones. Those are producing ionic. Ionic means they are producing ions. Those are producing what? When dissolved H2O. So those are soluble, like dissolved like, correct? And we took another one that's unpolar solutions. We took cyclohexane. Can I take this one out? Can I take this one out? Take it, okay. So we took the unpolar solution here, unpolar solution, or solutions here. We took the solvent here, cyclohexane, solvent here, and here's the solute. So we took cyclohexane is our solvent. Cyclohexane, and we took iodine, correct? And cyclohexane looks like this one here. It's a cyclic, but not aromatic. It's C6H12. So then you have all this here, all those here, all single bonds, all this hydrogen here. So 12 hydrogens. So you have, this is non-polar solvent. I just draw that to show you that's cyclic. Cyclo means cyclic. That's a cyclic. So with iodine, it's soluble. So that's very nice. Iodine is soluble in iodine. And I'm not sure what's the other compound we took out. We took oil. So we took oil here. Oil. And it came out to be what? Soluble. So today we'll have the opportunity to solve. But cyclohexane will not dissolve salt or ionic compounds such as potassium nitrate or even covalent like sugar or permanganate. It's not soluble. Only those non-polar. So all those are non-polar solutes. So you will see that the polar solvent will dissolve polar solutes, and the unpolar solvent will dissolve unpolar solutes. Okay, guys. So that's what we did last week in the lab with section 062. Today's section 058 will do the same, but the other section, because we are about large number of students. They split the students in 2 sections for the labs. So, any question? Now, there is some solubility rule. That's the chart I want to have it printed for quiz number, the last quiz number 4. Can I take this one out? So, what you want to do here, maybe I will find you another chart, maybe better one. You see what are soluble, what's you regarded soluble, what's you insoluble. And all this about in H2O. We are looking this, our solvent comparison is H2O as a solvent, H2O as solvent. So you will see that group 1A and ammonium are always, the cation are always soluble regardless. So group 1A, it is group 1A plus ammonium are always soluble. 1A means you have lithium ion, you have sodium ion, you have potassium ion, all the way to francium, cesium, whatever, to francium ion. Those cations are soluble, and the ammonium plus the ammonium. Those are soluble. Regardless, wherever you put the anion, the negative one, the anion, put them the covalent anion, the non-metal ones, it's not will be insoluble. It's always soluble in H2O. This you have to visualize. Now the insoluble anions, that's soluble, correct? Then this is 1. 2, all nitrates are soluble. Number 3, all acetates, CH3, COO minus, it's minus, are soluble. Number 4, halogens Now, when it comes to halogens, then we have exceptions. Halogens means chloride, bromide, fluoride before it here, iodide. But we have exception here. You have to know what the exceptions are, correct? So the same thing with sulfate. Sulfate are soluble, except they have some exception. We'll look at the exception together with ourselves. Always the exception will be lead 2, silver 1, and mercury 1. So we will look into that. Thing and look to insoluble. Carbonate are all those carbonate are insoluble. Anytime I have, except when they come to this, they will be soluble. But any carbonate connected itself with another cation, not the first one, but with any other cation from other groups, not the first group, they will be insoluble. Carbonate, the sulfides, the phosphate, the chromate, the dichromate, Cr2O7 2 minus. All those groups are not soluble, okay? Except when they connected themselves to first group or ammonia, okay? So this is just a general one, and in the ACS exam they give you a very simple one that you are used to it. So can I take this one out? Take it out. Okay. So let me. I might think I just, if I forget this, remind me with this. So in iCollege there is one, but let me just get out of iCollege here. But in iCollege there is one here, but one like this. This is the one you are looking for. This is the one you are looking for. If I take this one here, copy it, and layout. Okay, guys, so here it is. You have to. So, guys, I wanted to print this one out for you for your information, so you can understand the solubility issue, correct? So you can look at all those are. This is the rule of soluble. This is the rule of not soluble, and all those here insoluble, correct? Hydroxide in unstable, but they have exceptions when there are exceptions there. So barium hydroxide is soluble, strontium, calcium, correct? Tellur is soluble. So all those are exceptions. So maybe I find you one is easier to visualize the ions. So, and I think it will be wise if we look together to this is, you can print it out, and I will try to find you another even better one. So let me get into the hold on. Let me get into the solubility. I need to solve some problems. Solubility. What was the key? Worksheet. We don't need the answer. We look at the answer itself from the table together. So solubility worksheet. Let's see here. We need something free, not to pay any money. So just look and okay, this is like an exam quiz. That's I need to see if I can combine some compounds together to see if they are soluble or not. Yeah, let's look at this. This is a good one. Let's take this one out, everything. Um, it did not give us. Here it is. Okay, guys. Let's look at this and tell me how many we have. We have 10 from 1 to what? No, that's more than, yeah, 10. The first one, magnesium phosphate is soluble or non-soluble? So that's the reason we need help with this, what? With this, so magnesium sulfate. Magnesium is not group 1A, correct? So group 2A is 2, or group 2 or group 2 mostly are soluble if they have nitrate, acetate, you know, uh, but not other stuff. So all the sulfates are what? Somebody will tell me from the table? Are insoluble, correct? How about magnesium? Magnesium sulfate. Is there any exception? No, there's no exception. So magnesium sulfate then will be, guys, what will be our answer here? What will be our answer? Soluble or non-soluble? Come on, guys. Don't let me down. Anything said magnesium combined with sulfate of phosphate is soluble? No. So the first thing here, this one here will be, come on, guys. I know it's Monday, it's hard. So this one will be insoluble. Potassium hydroxide is soluble or non-soluble? Potassium group 1A, correct? Or 1? Soluble? Yes. Soluble. Nickel chloride. Nickel chloride. All the halogens are soluble except the 3 ones. Sulfur, lead, and mercury. So here it is. Yeah, silver, not sulfur, silver. So here it is. Where is it? So halogens, here they are. Here they are. That's always soluble, except when they connect themselves to those cations. Correct, guys? So those are not soluble. But nickel is not exception. There's nickel. Nickel will be soluble. Nickel will be soluble. So you get the idea. So that's type of questions we'll ask in the SS exam and in our quizzes. Let's take this one out. Okay, guys. So let's take this one down. Just back to this one here. So how about this one? We said what's soluble, correct? One more, maybe one more. Yeah, we'll do one more. So which one you like? Nickel, we said soluble, correct? How about ammonium hydroxide? All the ammonium cations are what? Soluble. So it has to be soluble. Mercury 1 sulfate. Mercury 1 sulfate. Mercury 1 sulfate. All the sulfates are what? Soluble. Sulfates are soluble, except when they connect themselves back again to our. So where is the sulfate, correct? Sulfate is here. They are always soluble. That's what we said. But there is exception. Sulfates are always, what their exception? When they connect themselves with those type of ions, correct? Mercury 1. So then I have to go back and look at the question here. The question says mercury 1 sulfate. Well, mercury 1 sulfate is included in the exception here, correct? This is mercury 1. This is mercury 1. It's mercury 1 or mercury 2? Yeah, mercury. Oh, mercury. This is mercury 2. Mercury 2. And I think mercury 1 is not soluble either. So The answer is they are not soluble. So except mercury 2. Okay. So mercury 1, this is mercury 1, guys. This is mercury 2. So mercury 2 is insoluble, but mercury 1 is soluble. So let's look at this. Let's answer this one here, guys. So let's take this one here. We say it again. Let's put this one here. This is not soluble, soluble, soluble. This is soluble. This is mercury 2, correct? Mercury 1 because sulfate is 2. So this is soluble. Mercury 2 is insoluble. Mercury 1 is soluble. So potassium bromide, you have potassium soluble. Lead carbonate is not soluble. Lead iodide is not soluble. Those halogens, when they come to mercury 1, lead, silver ions, they are not soluble. Barium sulfate is slightly soluble or insoluble. And nickel chloride is soluble. So you have to have this table handy in your hand to understand the solubility. Are you following me here? Just to let you know. So look at I know at the beginning it will be hard to visualize, but then you look at the table and look, it's like, like a puzzle, You are playing a puzzle. You add this to this and see, go to the table if they are really combining and they are soluble or not soluble. That will tell you the table. So I will try to get you one that's really maybe beside this one. You can print both of those and keep them handy. It will help a little bit. So this one here, you can print it out, and then I'll give you one maybe much better than this one here. Okay, guys. So let's take this one here, and this is an example here. Now we'll have the solubility. When it comes to solubility, we have 2 types or 3 types of ionic compound. We are looking for the ionic chemical equation. So let me take this one out. So types of chemical equation. That's all about solubility. Types of types of chemical or ionic chemical equation or chemical equation, just write chemical in general. We have the first tab is the first tab called molecular or because we are looking at ionic molecular ionic or molecular the second tab is a complete ionic chemical equation, and the third is net ionic chemical equation. So we are looking at those here, and then we can. I have the molecular the ionic molecular equation here. We can add ionic here. That's fine. Ionic molecular equation. So we have lead nitrate aqueous plus sodium chloride. Aqueous gives you lead chloride. Solid plus sodium plus sodium aqueous. So this is ionic molecular equation. This all ions, ionic compounds, correct? So aqueous means dissolved in H2O, and S is solid, and AQ is aqueous, is soluble in H2O. G for gas, L for liquid, correct? So the complete ionic we have to take apart. We have to take apart all the aqueous. So take apart. Those are taken out. The solid, liquid, and gas are kept by themselves. So solid, gases, and liquids are kept intact. This is one of the rules. Second, take apart all aqueous ionic compounds. Okay, guys? So, and I'm taking this one out here. Let's take one for the time being out. Come back to it. I need the space here. So, complete. AQ. Those are ionic, so I will take them apart. Then I have here lead. This is 2 here, by the way. So, and we have to balance it. So 2 chloride, I put 2 here, correct? And I have nitrate 2, sodium 2, so I put 2 here. So this is 1 to 2 to 1 to 2. This is the mole ratio or coefficient ratio. So let's look at this. This has AQ. This one has AQ. This one has AQ. Let's take it apart. So lead. So I have lead 2 plus aqueous plus 2 nitrates at the bottom, 2 NO3 minus aqueous plus 2 sodium aqueous plus 2 multiplied by chlorine, 2 chloride aqueous will give us lead solid, keep it intact, we do not take it apart, correct? Plus 2 sodium aqueous plus 2 nitrate aqueous. This is called the complete ionic chemical equation. We took apart all the aqueous compounds soluble in H2O and keep any ionic compound that is solid or gas or liquid intact, right? So now the net ionic will come. The net ionic will come here. Will discard or delete all spectator ions. What do you mean spectator ions? Those ions appearing in the both sides of the equation. They are there inside the solution but are doing nothing. They are not contributing to the reaction. So ions appear at both sides of equation. So which one now? You tell me which one is the side. Let's lead. There's no lead 2 plus, and there's the lead is here. So with this, so lead is not appearing. So how about nitrate? Well, nitrate is 2 nitrate here, and 2 nitrate here will cancel out. That's a spectator ion. That's spectator ion. We have to get rid of it. 2 sodiums and 2 sodiums. That's another spectator ion. The only left is the net ionic chemical equation. This is number 3. Net ionic chemical equation will be lead 2 plus aqueous plus 2 chloride. Aqueous will give us lead chloride solid. This is the net which we have. We have discarded all the spectator ions. We have discarded all spectator ions. This is 3 type of ionic chemical equation there. So first you have the whole ionic as they are, molecular one, don't take them apart. Second one, you look at the AQ only, subscript AQ. Those aqueous, take them apart, leave any solid. So we left, this is solid here. See here, this is solid. We kept this solid compound by itself, we'll not touch it. If it's liquid, we'll keep it as is. If it's gas, we'll keep it as is. Okay, guys? So then at the end, you take just the ions appearing on both sides, those spectator ions. They are there, but they are chemically not active. They don't contribute to the overall reaction. The whole reaction is between lead cation and the chloride anion to give you lead solid precipitate, white solid precipitate, white solid precipitate. Can I take one out? Take it out. Out, everybody has it? Okay, let's see here. So here's an example here, guys. You can see they have this molecular ionic chemical equation, and then the complete ionic chemical equation they start taking apart. This is the complete one. This is the complete one, and the net. Then you have to get to look at the. We have nitrate the other side. That's your arrow here. This is 6. This is 6. That's spectator ion. Sodium 6. Sodium 6. So the real reaction is between phosphate and calcium to give you the solid one. This is the net ionic chemical compound, correct? So you add those two to get you this, and those that you can take them out. So any question? So I can write it here for you. 2PO4 3 minus plus 3 Ca2 plus aqueous will give us Ca3PO4 2 solid, white solid. Okay, guys? So that's the net ionic. That's the net ionic equation. So let me just can I take this one out? That's just an example here. And see the net ionic came out. Can you see it? Yeah, whatever we said, we discussed that together. We said this is the complete ionic. Then they start taking those spectator ions. Yeah, the sodium the side and sodium the other side, and nitrogen on this side, nitrogen side, and this is the net ionic chemical equation. Correct, guys? So okay, guys. Okay, so now we'll come to math. We'll come to some concentration. So we have to look into these formulas. I wanted to print this one out, so in the way you can understand the whole thing when it comes to the calculation. So let me show you and memorize those rules. So let me take this one here out, and now is the last topic in this chapter is concentration. It is, guys. Okay, guys, concentration. We have plenty of formulas. We took some of them already in the lab, so but some of them might not be taken in the lab, but we have taken most of them in the lab, I think, but some of them might not be taken. So the first is mass over the volume percent. Okay, this is the first formula. This formula here will tell you mass of the solute in grams over volume of the in gram of the solution in ml, and the whole thing multiplied by 100%. Okay, guys? So, in this case, the mass, this is solid here. This is solid. This is liquid, which is the solvent itself. Now, second one, mass over mass percent equal to mass of the solute mass of the solution multiplied by 100%. However, mass of the solution, you have to be careful here. Mass of the solution is mass of the solute plus the solvent. So this one here is replaced by mass of solute plus mass of solvent. Of course, this is in grams. This is in grams. So the unit of this is gram per ml percentage. This is the units here. Percentage, and this is gram over gram percentage. Okay, guys? So the second one is you have to include both. You have to include this, and you have to include this one here. Both of them. Mass of the solution. In the top here, volume of the solution is this volume of the what? Of the solvent, because the solute is what? Is solid. So, can I take this one out? Take it out? Okay, let's do volume to the volume percentage. So unit ml divided by ml percentage. That's the unit. So the law is, the formula is volume to volume of the solute volume of the solution multiply by 100. Now, volume of the solution, you have to be careful here. That means both. So this one here will be volume of the solute divided by volume solute plus volume of a solvent. And the whole thing here multiply by okay, guys. So we have mass mass over the volume, mass over mass, volume over the volume. Mass over mass, you have to watch. That's mass of the solute and the solvent at the bottom. Volume of the solution, volume of the solute plus volume of the solvent, both. Okay, guys. Now, one more. We have a couple more. That's done. That's it. So now we'll do something called molarity. Something called what? Molarity. The unit here is 3 units, capital M, molar, or mole per liter. So it has 3 units. They are the same thing. Sometimes capital M, sometimes molar, sometimes mole per liter. But for our calculation, this is the best because we can follow the calculation with it. So for calculation purposes, okay. So the molarity is a ratio. All this, the formulas in chemistry and physics are really ratios. So the molarity is ratio between what? Between mole of the solute divided by liter of the solution, volume, liter of the solution, mole per liter. So it says mole per liter. So the mole itself is defined as a ratio as well. So that's another mole. You can write it here. Mole of the solution is a ratio too. Will be mass of the solute divided by molar mass of the solute. Molar mass of the solute. Okay, this is grams. This is gram per mole. The gram cancels out, the moles underneath, the mole go up. Okay, guys? Okay, so two more. Very quiet today. It's like a real, absolutely Monday today. Nobody talks, nobody whispers. I hear nothing today. That's okay. I hope by the time we come to the lab, everybody will be awake. So anyway, because we will be using the burner, the flame, so we have to be real awake. So anyway, so molality. What is now? You see the molality here? Molality AR. Molality. Then you have to take the AR out. Correct? Molality. So let's take this one here and see the units of this. Can I take this one out? So let's take this one out. So molality. We took AR out. And the units, again, 3 units, the same thing. Small m, like a mass, or like meter. Small m has a lot of usage, so a lot of usage. So usage, it is used everywhere. So m, meter, m, mass, and m is molality. And then you have, we said small m, and then the second one is uh, mole per kilogram solvent. This is mostly used. And the third one, we have what we have in the units of molarity. We have capital M, molar, correct, molar, and then mole per liter. And here, instead of molar for molarity, we call it what? Molal. Okay, so 3 units. M, mole per kilogram, and that's used for the calculations, and molar. So, and the definition is mole of the solute, again, is ratio per kilogram solvent. And mole of the solute, you know that mole of the solute is mass of the solute divided by the molar mass of the solute itself. Okay, guys, I think we have. I have 1 minute. Can we go for the deletion? Well, okay, I'll give you time. It's Monday. We can catch this minute in Wednesdays. Okay, guys. Thank you very much. Dr. Jane, you say to me, Peter Zare. Okay, Peter Zare. Yeah.